Lecture 11 on linear regression. This relies heavily on Lecture 10, which involves relating two numerical variables. And I'll remind you, we talked about scatter plots, and we talked about the coefficient of correlation R, or rho. Before we can return to those topics, I need to remind you a little bit about how equations of lines work. So remember, we generally write the equation of a line as y equals a plus bx, where b, which is the coefficient of x, is the slope. Geometrically, it's the amount y increases, or decreases, if it's negative, each time x increases by 1. And a is the y-intercept, which is the value of y when x is 0. So when you look at an equation of a line, you can interpret it geometrically very straightforwardly. A is where the line crosses the y-axis, and b is the amount y increases when x increases by 1. So you can draw the line just by looking at a and b. I have to make an apology here. The notation is unfortunate because in mathematics, at least in calculus, you probably remember, lines were generally written as mx plus b. So it differed both in that the coefficient of x is usually written first, which isn't much of a big deal, but second in that that coefficient was called m, not b, and the y-intercept was called b, not a. So b is getting used to mean the opposite thing. Even worse, this is a much more statistics convention, but even worse, it is almost as common in statistics to write y equals ax plus b. So there's no uniformity here. I am following the book's notation and will try and stick to it rigorously, although I will get you used to it being written with the x first and the x second, because that's something you should get comfortable with. But in general, you should expect different variations on this notation. So we'll always call it b, the slope, but outside the classroom, all bets are off. The least squares line is the line that we will care about. It was first described by Carl Friedrich Gauss, who lived 1777 to 1855. There's his picture, and he is, most people would say, the greatest mathematician of all times. All sorts of mathematics is named after him. The least squares line isn't, but perfectly well could be. It is a method for finding the line of best fit for data. Data meaning for two numerical variables being related. It is used throughout mathematics and the sciences, one of the most important tools in quantitative fields. Here's how it works. I want to step back, and I want to think about taking any line that you think might fit the data and deciding how well it fits the data. So imagine you have a line, y equals a plus bx. It's your candidate for the line of best fit. And you've got some data. Let's say one of the data points is x1, y1. Well, it's not too hard to decide how well the line fits or explains that point. If you plug x1 into that line, you should get y1. So the quantity you actually get is the predicted value for y1. What this line tells you y1 should be, we call that y1 hat. And it is a plus b times x1. We're just plugging the x value in for x. The residual is the error. That is, the actual value of y minus the predicted value of y. So it's y1 minus y1 hat, which I've expanded out there. That tells you how well the line did at predicting that point. So there's a residual for each data point. Some of the residuals will be positive, some will be negative. So if we want to measure how well collectively it did, we can't just add up all those residuals. They might very well add up to 0. Instead, we will add up the squares of the residuals. So remember that sigma notation, that giant E-looking object, tells you to take every number from I equals 1 to n and plug it into the following formula. That is, for each I from 1 to n, you're going to take the residual, yi minus yi hat, and square it. And you'll add all those up. That is called the sum of squares error, because it is the sum of the squares of the errors. We're going to take that as a measure of how well the line fits the data. The smaller that is, the better. How do you find the line that makes that quantity the smallest? Well, you remember from calculus that you learned how to optimize. You learned how to make the cost or the area or the length as small as possible. This is a variation on that idea. It's slightly more complicated, but it is a straightforward problem in multivariable calculus to find the line that minimizes the sum of square error. It has two properties which effectively give you the formula. And now you see at last r shows up. The first property is that the slope, b, is the standard deviation of y over the standard deviation of x times r. In the population context, we would use beta, the Greek letter ancestor of b, to represent the slope. That's the Greek version of the slope. And we would replace the sample standard deviations with population. And remember, r is the sample coefficient of correlation, rho is the population coefficient of correlation. This equation actually makes a fair amount of sense. R is sort of like the slope. It's positive when the slope is positive. It's negative when the slope is negative. But R goes from 1 to -1, whereas the slope always has units that are the units of y divided by the units of x. That is to say, if x is the number of customers and y is dollars of sales, the slope, the amount y increases each time x increases by 1, is dollars per customer. So we need to turn r into something with units of y over units of x. And remember, the natural units to look at your data set in is the standard deviation. Okay, so that's the formula for the slope. Of course, you need to compute r to get that. The second fact is that the least squares line always contains the point average of x, comma, average of y. That, of course, is the middle of the data in a very reasonable sense. So it always goes through the middle of the data. And remember, knowing a point and the slope is enough to give you the equation of the line. Here's how. The y-intercept is y bar minus bx bar. And here I've expanded it in terms of r. I may ask you at some point, I may give you r, sy, sx, x bar, and y bar, and ask you to find a and b. That's the most I will ask you to do by hand. Mostly we will have Excel line. Okay, so if the data are linearly associated, there's a lot hidden in that assumption, which we won't really talk about. Later in the semester we'll talk about it a fair amount, actually. If the data are linearly associated, then the least squares line, y hat equals a plus bx. I'm going to put the y hat there because it is the predicted value of y when you plug x into the line. Y hat tells you the average value of y for the given x. So its predicted value of y is in fact the average among all those values of x. As I've said before, almost no data is linear if you run through all possible values of x. So even if the data you're looking at looks linear enough that a least squares line makes sense, extrapolating that least squares line beyond the range where you have data is always a terrible idea. So the interpretation, both the slope and the y-intercept of the least squares line, if we combine how you interpret the slope and y-intercept of a line with what the least squares line is doing in terms of prediction, you get the following interpretations of the slope and y-intercept. These are really important. These are the basic qualitative takeaway when you've done a least squares line. So the first and most important is that the slope b is the average amount you expect the response variable y to increase each time the explanatory variable x increases by 1. This is, we'll see in examples, the best description of the relationship between x and y. Best way to summarize how x and y are related. Less important, but sometimes important, is the y-intercept, which tells you the average value of y when x equals 0, the average response value when the explanatory variable is 0. That only makes sense when x equals 0 is part of the range for which you have data, otherwise it gives nonsense. And we will see situations where you plug x equals 0 in, the y-intercept is negative, even though there's no way y can be negative. While we're on the subject of interpretation, I have to talk about r squared. When we calculate the least squares line, we will usually not calculate r, we'll instead calculate r squared. It contains almost the same information. Of course, it forgets about the sign of r, so there's a loss there, but usually you know the sign of the relationship, so that's not very important. But the advantage of r squared is that it has a precise, though subtle, interpretation, which I will expect you to know and be able to give in a given problem. R squared is the percentage of variation in y that's explained by its linear relationship with x. That's kind of a complicated thing. Before I go on, I should say that r squared is the best measure of how well the least squares line does at predicting y. Let me give you an example. If you're trying to predict y, people's GPA, using x, their IQ. If you're just guessing somebody's GPA without knowing anything, it could be anywhere, some reasonable guess, maybe 3 something, and you wouldn't be surprised to be off by a whole point of GPA or something like that. If you know somebody's IQ, you plug it in the least squares line, you get a better guess. And you'd expect your error to be smaller, right? You've reduced the error by gaining information. The more intelligence affects your GPA, the more information knowing somebody's intelligence gives you about the GPA, and the smaller the error. So that's what r squared measures. Variation really means variance, which has a technical meaning here, which we won't talk about. But the idea is it's the percentage of all the variation that's possible in y that is explained by its linear relationship with x. If r squared is 80%, that's saying once you know the IQ of somebody, the variation that you can expect to see in their GPA is 20% of what it was before. Again, technically the variance. So you've reduced your ignorance by 80%. You've reduced it to 20% of its former size. Let's see what these look like in some more concrete examples. So let's first look at how number of customers each day affects sales in hundreds of dollars in some store. Take a moment, pause if necessary, to make sure you understand what the explanatory variable x is. It's, of course, number of customers each day, and the response variable y is the sales in hundreds of dollars. So let's say we look at our data and we get a least squares line y hat equals 5.2x plus 0, and we get r squared of 0.85. What does that tell us? The slope, 5.2, tells you that for each additional customer, you can expect, on average, to have $520 more in sales, which suggests that on average each customer buys $520 worth of stuff. And you have to agree that that is the best description of how customers relate to sales. So a customer walks in, on average you can expect to see $520 worth of sales. That y-intercept of 0 is suggesting to you that if there are no customers, your average sales will be 0 that day. That seems pretty reasonable. The r squared of 85%, or 0.85, tells you that 85% of the daily variation in sales is explained by the number of customers. The other 15% involves things unrelated to the number of customers, the weather, the economy, how much advertising you did. All those things may make customers more or less willing to purchase once they're in the store. Here's a second example. Suppose in your house you want to predict how much gas you're going to use in a day. That's measured in thousands of cubic feet, based on the average temperature in Fahrenheit outside. So then, of course, we have X is the average temperature outside doing the predicting, and Y is the gas use, which is being predicted. Let's say that we get a least squares line Y hat equals 16.4 minus 0.24x, and we get an R squared of 0.91. What does that tell us? Well, the y-intercept tells us that on a 0-degree day, we can expect to use an average of 16,400 cubic feet of gas. That's assuming we have data that goes down to 0. So if you live in Maine and your data includes winter, it probably goes down to 0, and that's reasonably accurate. If you live in Florida and your data never got below 40, then that's a meaningless number. But the slope, regardless, is meaningful because that minus 0.24 is telling you that each additional degree outside saves you 240 cubic feet. In other words, it takes 240 cubic feet of natural gas to raise the temperature of the house 1 degree. That is a very precise description of the relationship. In fact, it will tell you that engineers, the quantity they use to describe the heating efficiency of a building is BTUs per degree. Number of BTUs it takes to raise a house's temperature 1 degree Fahrenheit or Celsius, which is almost what this is, except for the converting from cubic feet of gas to BTUs. Finally, 91% of the variation in gas use is explained by the temperature outside. What's the other 9%? How many people are home affects how much gas gets used to warm it up. Whether there are windows open or people open the doors a lot. What temperature, of course, people are setting the thermostat at, but also if you also use gas to heat your hot water and to cook with, most people who heat with gas do, then it involves the variation in how many showers you're taking and how much you're cooking, whether you're eating out. Okay, so here are the key things you should walk away from this lecture with. You should be able to explain what residual, least squares line, slope, and y-intercept are. Very important, you should be able to interpret the slope, and the y-intercept, and r squared in specific situations. I will ask you this a lot. And identify some key properties of the least squares line, like the fact that it goes through x bar, y bar, the fact that it's proportional to r, the fact that it minimizes the sum of the squares of the error. You should know what a residual is. We will talk in the future about the residuals now that we're focused on the least squares line. How far off a particular y value is from its predicted value will often be an interesting story. Okay, and with a little bit of time, we will go through and learn how to compute the least squares line and r squared in Excel. As I said, we'll never ask you to compute those from data by hand. You should be able to predict y from x. Once you've got the least squares line, you're just plugging x in. That's pretty straightforward, and you should understand what residuals are telling you in context. We will see that in some examples. See you next time.